Hello everyone, my name is Christian Sanchez and I'm going to show you my optimization project for the class Design Optimization at Embry-Riddle Aeronautical University. So, as a project we had to solve the following problem that is shown to you, which is a weight minimization of a 5-beam cantilever subject to a displacement constraint. The first step to do is to get the data that we are going to need in the next steps. So the first thing that we need is to know how many segments do we have, which type of element we are working with, and some of the properties of this element. So we know that there are 5 segments. This is a property that is given to us. We already have also an assumption here to get a simpler solution for this problem using the consideration that the thickness is really small. It's much less than the side, so it's considered to be neglected. Also, we have another property here, and as we are going to solve this by iterations, we will need a starting point, which the starting point for this problem is 5, 5, 5, 5, which means that we are considering that this cantilever uses just one tube of 5 as a side and 5L as a length. This is the starting point, and then we will try to minimize this and so on. So how to solve it? First, we have to use the assumption that is given to us. As I told you before, we have that the thickness of the tube walls is much less than the sides. So we can do the assumption that the thickness powered by an n, which an n is bigger than 1, is equal to 0. I'm sorry that I have a typo here, but it's not t bigger than 1, is n bigger than 1, that we will consider n t powered by n equal to 0. And so with this we already know that the volume of the tube is the following: is L multiplied by 4xt minus t squared, and we can neglect the t squared here. The t powered by 2 is equal to 0 here, so we are going to neglect it. We will just use this part to calculate the mass of this beam. And we also know that the mass is going to be calculated by the multiplication of the density per the volume of each segment. And so we will have the function f, which is on the right side. This function is the one that we are trying to minimize, but we need a condition. And we know that the condition is in terms of the deflection of the beam, so we need to first calculate the inertia that we are going to use in the following steps. So we know that the inertia of a square tube is the external side powered by 4 minus the internal side powered by 4, all this over 12. And Now, doing some calculations, as you can see, we can consider that the inertia will be 2 multiplied by xa powered by 3 multiplied by t over 3, because we are considering that every single t that is powered by an n bigger than 1 is going to be 0 or neglected. Okay, so the condition is that the deflection on this problem is going to be less or equal to 1. So we can't surpass this 1 deflection, and we know that the total deflection is going to be the summatory of each deflection of each segment on the beam. So we need to calculate the deflection of each segment, considering that the applied force is always applied on the end of the segment. And so we have uh, here the formula of the deflection of beams, and we do the calculus here, and we get that the formula of each segment of deflection is going to be F multiplied by L powered by 3 over 3 modulus Young and the inertia of the segment. We know that the inertia and the length are going to change in terms of each segment, because on each segment we have different values of areas, cross-sectional areas, and there are at different distances of the force. So the next step is to calculate each deflection on each segment, considering at first that the left side of each segment is fixed, and then we are doing some corrections here on each element. We are making the calculations from right to left. As you can see, we are making corrections because you know that the segments are, are are having a different deflection depending on the area and on the inertia, of course. So we have to make a correction because we are considering that after some distance we are changing segments. So that's why we are making this correction here, the correction here, here, and we are not making the correction on element 1, which is the end segment, the one that is not connected or joined to another segment on the right, just the one that are on the left and connected other ones on the right. So we already know that the condition is that the total deflection is equal or less to 1. I'm sorry that I have another typo here, but you know that is equal or less to 1. We already have the values of each deflection, which we know that for element 1 is 1 over x1 powered by 3. The element 2 is 7 over x2 powered by 3. The element 3 is 19 over x3 powered by 3, and so on. So we are going to use the sequential linear programming to solve this problem. And so we need the gradient vectors to do this. And also we are using the sequential quadratic programming, so for both we need the gradient of the functions f and g. G is the function of the condition and f is the one that we are trying to minimize. So taking the gradient, we have that the gradient of f is 4 rho lt, which is the derivative of x1, x2, x3, x4, and x5. As you can see here, is sequentially shown here as a vector. And the gradient of g is the derivative in the same order of x1, x2, x3, x4, and x5. As you can see, the derivative of x1 is here on the up part, and on the lower part is the derivative of x5. So now we will use MATLAB to solve this problem, which is with iterations. We are using a program that is given by our teacher or professor. This program needs the function that we are using, well, the functions that we are using, needs the starting point, needs some options, needs the lower boundary, the upper boundary, and the gradients of the functions to solve it. So as I told you before, we already have the functions, which are f and g. The starting point we already know that is set as 5 for every single x that we have. For the options, we are setting some properties of the program to be shown, in which some of them are like the tolerance that we are using, which is 0.001, and so on. For the lower boundary, we are using 0 as lower boundary because we are working with a real structural problem, and so we know that there is no chance to us to get negative values, as there are no negative dimensions or imaginary values. So is the important part here is that we are using 0 as the lower boundary, and the upper boundary we are using is infinite to make the iterations until we get a proper solution. And the gradient we already know is shown on the previous slide, which is the gradient of the function f and the function g. And we just run the program and get that the iterations made for SLP or sequential linear programming are 13, I'm sorry, and we get the values that are shown here at the bottom, which is x1 equal to 2.14, x2 equal to 3.52, x3 equal to 4.50, x4 equal to 5.30, and x5 equal to 6. Now, by using the same conditions but applying the sequential quadratic programming, we get 14 iterations, but we get different values, but similar. It's important to know this because as long as we are making optimization by two different methods, there must be some similarities. There must be almost the same value, but not equally the same. So we have here that x1 is 2.148, x2 is 3.5043, x3 is 4.4054, x4 is 5.258, and x5 is 6.072, approximating. Then we can replace on the conditions and decide which one is better to us. For example, I replaced the values and the values that I had on XQP. Oh, yes, on the sequential quadratic programming, uh, gave me a result that it doesn't fit completely with the constraint. I mean, it surpassed a little bit the constraint, but it was really small, the surpassing. I mean, the total deflection was 1.0001, which is basically not strictly inside the condition. However, it's a tolerance that you could consider if you are trying to minimize the problem. It's not that bad. And with the SLP, I had like an exact value of deflection of 1, which it was really good. But however, it depends on you, and you could decide which one to use. If you want to minimize despite it's not fully accomplishing the condition, or if you want to accomplish the condition but sacrifice a little bit of your minimization. So thank you everyone for paying attention, for hearing me, and I hope you can comment some of your doubts or any recommendations, and thank you very much.